Imagine if we could charge a cell phone in less than 10 seconds. Or imagine if we could have an electric car that travels for thousands of miles without having to stop and recharge for many hours. With supercapacitors and energy storage device, this is possible.
Supercapacitors are based on the electrostatic interactions between the ions and the electrode.
Supercapacitors offer numerous advantages, such as high power densities, service lives over 25 hours, efficiencies over 98%, and quick charge times. Just think of all the possible applications with these benefits. However, the main drawback of supercapacitors is that they have low energy densities, which means that they cannot store a large amount of energy. Furthermore, they have lower temperature operational windows, as they operate from only -40 to 70 degrees Celsius.
Now, how can we increase the energy density of a supercapacitor? Increasing the porosity of the electrodes can increase surface area, which directly increases energy density. Specifically, though, how can this be done? In the methodology I created for my research at the University of Texas at Dallas, I utilized two polymers with differing degradation temperatures, polyacrylonitrile or PAN and polystyrene or PS. When my polymers were subjected to high temperatures, the polymer with the higher degradation temperature, PAN, remained intact, while the polymer with the lower degradation temperature, PS, degraded to leave pores. This increased porosity to increase surface area to increase energy density. Look at that surface area now.
But there's more to it than just the electrode. The electrolyte used in a supercapacitor is just as important as the electrodes in increasing efficiency. Deputectic solvents are a new class of green and low-cost electrolytes that are based on a mixture of Lewis and Bronsted acids or bases. In my research, I created a novel DES based on the low-cost and environmentally friendly N-methylacetamide and lithium TFSI.
The formation of intermolecular hydrogen bonds in this DES lowered the melting point temperature of the electrolyte, which widened the operational temperature range of my supercapacitor from -50 to 110 degrees Celsius. This means my supercapacitor can store energy in developing regions with extreme temperatures, where 1.3 billion people live without electricity. The methodology utilized for my electrodes led to the first ever creation of parallel channels in supercapacitors. But why is this important? The channels allow for the ions to float more easily and increase the surface area by branching out to increase the energy density to 13.5 times greater than commercial supercapacitors. This low-cost, reliable, and wide-temperature range supercapacitor, the possibilities are limitless. It can be utilized in transportation industries such as in electric cars, or defense industries such as in military airplanes due to its quick charge times and high energy densities. We could even replace pacemaker batteries with a supercapacitor, which would reduce the amount of surgeries needed to replace the batteries.
With supercapacitors, we can have an energy revolution to change our world. Thanks for watching!